The research proposes a mini-batch method for solving nonlinear partial differential equations, PDEs, using Gaussian processes, GPs. This approach addresses the computational bottleneck of GP methods by applying a mini-batch algorithm. The method is based on stochastic proximal algorithms and reformulates the optimization problem to consider a small portion of samples at each iteration. This reformulation allows for the use of stochastic gradient descent, reducing the computational cost. The algorithm is designed to steadily reduce the error towards zero at a rate of O(1, k plus 1, m), where k is the number of iterations and m is the batch size. The method's novelty lies in its ability to scale with the number of samples, making it more computationally efficient than traditional GP methods. The paper also discusses the connection between the proposed method and existing GP-based methods, highlighting the advantages of this new approach in terms of scalability and computational cost. This paper introduces a novel mini-batch method for Gaussian process regression, which significantly reduces the computational complexity and memory consumption associated with traditional Gaussian process methods. The proposed approach solves an infinite-dimensional minimization problem by employing a representer theorem, allowing the computational cost to be reduced to O(m cubed) in each iteration. This is achieved through the use of a mini-batch approach, where the minimization over the latent vector z is considered in the optimization process. The author's convergence analysis demonstrates that the error decreases at a rate of O(1, k plus 1, m), where k is the number of iterations and m is the batch size. This mini-batch method is compared to other existing methods, such as those utilizing variational inference procedures, random Fourier features, sparse approximations, and stochastic gradient descent methods. However, the key difference lies in the treatment of the minimization over the latent vector z, which is not addressed in previous works like 7. The paper also revisits the general framework of the Gaussian process method for solving nonlinear partial differential equations, as proposed by 9. This involves solving a system of equations using a representer theorem, which allocates the burden of computations to each iteration. The proposed mini-batch method is then applied to this general setting, resulting in a more efficient and scalable solution. In terms of notation, the paper uses various symbols and conventions. For instance, given an index set I denotes its cardinality. For a real-valued vector v represents the Euclidean norm, and v(t) denotes its transpose. The inner product of vectors u and v is represented as less than u, v greater than or u(tv). For a normed vector space v denotes the norm of v. The paper also uses U to represent a Banach space associated with a quadratic norm, _U, and U denotes the dual of U. The duality pairing between U and U is denoted by, and the inner product of U is denoted by less than, greater than _U. The authors assume that the system of equations, 2.1, admits a unique strong solution in a reproducing kernel Hilbert space U associated with the covariance operator K. Here is a combined summary of pages 5 and 6 of the research paper. To approximate the solution of a Gaussian process regression problem, the authors propose a mini-batch method. The method involves defining a vector of functionals, phi, and a data vector, y, which are used to construct a nonlinear map, f. The GP method approximates the solution by minimizing an optimization problem, which involves a regularization parameter lambda and a data fitting term. The authors then abstract this problem into a general framework, considering a GP problem with nonlinear observations, and propose a mini-batch method to solve it. The mini-batch method involves reformulating the optimization problem into a regularized optimal recovery problem, which introduces slack variables, z, and a regularization parameter, beta. The authors then define a mini-batch version of the objective function, phi, which depends on a subset of the data, I. The mini-batch method iteratively updates the solution by solving a minimization problem, which involves the mini-batch objective function and a proximal term. The authors provide remarks on the method, including the fact that the restriction of Z to a compact set, X, is not restrictive, and that the method can be extended to incorporate a preconditioned variant. They also discuss how to compute the solution at a test point, X, and provide a representer formula for the minimization problem. The key equations in this section include the definition of the vector of functionals, phi, the nonlinear map, f, the optimization problem, the regularized optimal recovery problem, and the mini-Bach objective function, phi. The authors also highlight the importance of the Cholesky decomposition and the computational cost of the method. Here is a combined summary of pages 7 and 8 of the research paper. The authors present a mini-Bach method for Gaussian process regression, which involves solving a sequence of optimization problems with smaller sizes of matrices to be inverted, reducing the computational cost to O(m cubed). The method is based on a sampling operator S_i, which maps from the function space U to the sequence space L2, I, where I is a subset of indices. The authors establish a representer formula for the optimization problem, which involves solving a linear system with a matrix of size m, enabling efficient computation. The authors also provide a convergence analysis of the mini-Bach method. They introduce some basic notions of convex analysis, including weakly convex and strongly convex functions, and define the proximal map and Moreau envelope. They establish a crucial inequality for the convergence analysis, which shows that the objective function value at the approximate solution is bounded by the objective function value at the true solution minus a term that depends on the gradient norm. The authors then define the notion of stability for the optimization problem, which involves perturbing the indices and studying the behavior of the approximate solution. They show that the stability of the algorithm is crucial for the convergence analysis. The authors also discuss the implementation details of the algorithm, including the use of block diagonal matrices to reduce the dimensions of the unknown variables and the choice of the nugget parameter eta. They remark that the use of block diagonal matrices allows for smaller nuggets and more accurate results. Overall, the authors present a novel mini-Bach method for Gaussian process regression, which reduces the computational cost and enables efficient computation. They provide a convergence analysis of the algorithm, which is based on the framework of convex analysis and stability analysis. Given gamma greater than 0, we define an operator G pro xi psi, gamma by G pro xi psi, gamma, z, equals argmi nu element of U, z element of x psi, U, z, I, plus gamma 2, z minus z, 2, for all z element of x. This operator is E stable for some E greater than 0 if the approximation of E xi, psi, ui, z, xi. Using a mini-Bach is bounded by E on expectation. We also have a lemma showing that if G pro xi psi, gamma is E stable, the approximation of E xi, psi, u, z, xi, using a mini-Bach is bounded by E on expectation. This stability is crucial for the convergence analysis of algorithm 1. The algorithm's convergence is studied under the assumption that all linear operators in 2.6 are bounded and the functions phi in 2.6 are continuous differentiable. The weakly convexity of phi I, defined in 2.8, is established, which directly implies the convergence of algorithm 1. The stability analysis and weakly convexity property are key components in this convergence study. In this paper, the authors introduce a novel mini-Bach method for Gaussian process regression, which significantly reduces the computational complexity and memory requirements compared to traditional methods. The proposed algorithm utilizes a stochastic gradient descent approach with a mini-Bach of data points sampled from the dataset. The authors prove that the sequence generated by the algorithm converges to a nearly stationary point as the number of iterations and batch size increase. They also demonstrate the efficacy of the mini-Bach method through numerical experiments, solving a nonlinear elliptic equation and Burger's equation. The experiments are conducted using Python with the JAX package for automatic differentiation, leveraging information between points in each mini-Bach by taking nearby samples. Here is the combined summary. The authors present a mini-Bach method for Gaussian process regression, applied to nonlinear elliptic and Burger's equations. In the nonlinear elliptic equation, the true solution is prescribed as sin pi x1, sin pi x2, plus 4 sin 4 pi x1, sin 4 pi x2, for x equals x1, x2, element of omega. The Gaussian kernel with length scale parameter sigma equals 0.2 is chosen for regression. The algorithm uses n equals 1200 samples in the domain, with n omega equals 900 interior points, and stops after 40,000 iterations. The technique of eliminating variables at each iteration is employed, and the resulting nonlinear minimization problem is solved using the Gauss-Newton method. Figure 1 shows the results of the mini-batch GP method with a batch size m equals 64, illustrating the samples, loss history, true solution, numerical solution, and pointwise errors. The mini-batch approach achieves accuracy comparable to that of the GP method using the entire samples. In the Burger's equation, the authors consider the nonlinear partial differential equation with nu equals 0.2 an unknown solution u. The anisotropic kernel is chosen with parameters sigma 1, sigma 2 equals 0.3, 0.05. The true solution is computed using the Kohlhoff transformation and numerical quadrature. The algorithm uses n equals 2400 points uniformly in the spacetime domain, with n omega equals 2000 interior points. Figure 2 presents the results of the mini-batch GP method with a batch size m equals 75, showing the samples, loss history, true solution, numerical solution, and pointwise errors. The authors use the technique of eliminating constraints at each iteration and the Gauss-Newton method to solve the resulting nonlinear quadratic minimization problem. Throughout the experiments, the nugget eta equals 10 is used. The results demonstrate the effectiveness of the mini-batch GP method in approximating the true solution of the Burger's equation. The paper introduces a mini-batch method for Gaussian process regression, which allocates the computational cost of GPs to each iterative step. This approach is particularly useful in solving nonlinear partial differential equations, PDEs, with Gaussian processes. The authors present a rigorous convergence analysis of the mini-batch method, providing insights into the choice of batch sizes and their impact on convergence rates and solution accuracy. In the numerical experiments, the authors solved the Burger's equation in a nonlinear elliptic equation using the mini-batch GP method. They observed that increasing batch sizes results in faster convergence rates and smaller losses, as demonstrated in Figure 3. The choice of mini-batch sample points significantly influences the performance, suggesting future work on investigating different sampling techniques. The paper also includes a detailed proof of key lemmas, such as lemma 2.5 and lemma 3.6, which are crucial for establishing the convergence properties of the mini-batch method. These proofs involve showing that the objective function is Lipschitz in a bounded set, and that the minimizer of the objective function satisfies certain conditions. The authors conclude by discussing potential extensions of their framework to more general GP regression problems, such as semi-supervised learning and hyperparameter learning. They also acknowledge the importance of selecting effective sampling techniques for mini-batch points, as this can significantly impact the performance of the algorithm. The paper discusses a mini-batch method for Gaussian process regression, focusing on the stability and generalization of the model. It introduces a new method for approximating the Gaussian process, GP, posterior using mini-batches, which is shown to be E-stable. The method leverages the properties of the GP to ensure stability and optimality. The proof of proposition 3.8 is provided, which demonstrates the convergence of the mini-batch method. The paper also references various works on stochastic optimization, weakly convex functions, and Gaussian processes, highlighting the importance of better models in stochastic optimization. The summary concludes by emphasizing the significance of the method in achieving stability and generalization in Gaussian process regression. Here is the combined summary of pages 19 and 20. This paper proposes a novel mini-batch method for Gaussian process regression, addressing the computational challenges of large-scale datasets. The authors draw inspiration from the literature on hyperparameter optimization, scalable Gaussian processes, and physics-informed neural networks. The method is rooted in the concept of proximal duality, leveraging the work of Murrow, 1965, and Nemirovsky et al., 2009. The authors develop an iterative algorithm that alternates between a primal update and a dual update, utilizing the sparse Cholesky factorization approach of Schaefer et al., 2021. The primal update involves solving a stochastic optimization problem, where the objective function is approximated using a mini-batch of data points. The dual update, on the other hand, involves updating the dual variables using a gradient-based approach. The authors also discuss the connections between their method and other approaches in the literature, such as sparse Gaussian processes, physics-informed neural networks, and numerical methods for solving nonlinear partial differential equations. The mini-batch method is demonstrated to be computationally efficient and scalable, making it suitable for large-scale datasets. The authors provide a theoretical analysis of the method, establishing convergence guarantees and bounds on the error. The paper also presents a review of the relevant literature, highlighting the contributions of various researchers in the fields of machine learning, Gaussian processes, and numerical methods. The author's approach is situated within this broader context, offering a novel solution to the challenges of large-scale Gaussian process regression.